Hey there, let's talk about something that's happening all around us and even inside of us, like right now, seriously. If you've had a banana lately, you've experienced it. They're actually naturally radioactive. We're talking about 15 atoms decaying inside a banana every single second. It's the same process that powers the very core of our planet, helps us date ancient history, and even lets us see inside the human body. We're talking about radioactive decay.
So let's kick things off with a little puzzle. What is the one thing that connects, say, an ancient dinosaur fossil, the famous Dead Sea Scrolls, and a modern cancer therapy scan? I mean, they seem totally unrelated, right? Well, the answer is the exact same powerful natural process, radioactive decay. And stick with me, because you're about to see exactly how it all fits together.
So where does all this start? Well, it all begins with something incredibly tiny. A single atom that's, well, a little bit shaky. It's unstable. And at its heart, that's all radioactivity really is. It's not some crazy, chaotic explosion. It's just an atom on a quest to find a more comfortable, more stable way to exist.
Okay, so here's the official definition. Radioactive decay is the spontaneous change of an unstable nuclide, and nuclide is really just a fancy science word for a specific kind of atom, into another one. As it does this, it releases a little bit of energy. You can think of it as nature's way of just chilling out.
You know, to make this easier to understand, scientists have this really great analogy. They call the original unstable atom the parent. And when that parent decays, it doesn't just vanish. No, it transforms into a new, much more stable atom that they call the daughter. So, see, it's not about destruction at all. It's all about transformation.
So how does this change actually happen? Well, it's not a one-size-fits-all kind of deal. An atom actually has a few different roads it can take on its journey to stability. You can almost think of them as different flavors of decay. So yeah, there are a few ways this can go down. An atom might spit out what's called an alpha particle, which is basically a tiny helium nucleus. Or it could go through beta decay, where a neutron in its core flips into a proton and shoots out an electron. But listen, you really don't need to memorize all the nitty-gritty physics here. The most important thing to get is that each one of these pathways is a specific, predictable step that gets that atom closer to being stable.
And that word, predictable, that's where this gets really interesting. Because here's the thing. We have no idea when one specific atom is going to decay. It's totally random. But if you get a whole bunch of them together, we can predict with incredible accuracy how long it'll take for a large chunk of them to change. And this gives us what is basically nature's own universal cosmic clock.
So how do we measure the ticking of this amazing clock? We use something called a half-life. And all that is the time it takes for exactly half of the radioactive parent atoms in a sample to turn into those stable daughter atoms. Now here is the absolute key. For any radioactive element, its half-life is a constant. It never, ever changes. It's one of the most reliable numbers in all of nature. Okay, this explains it perfectly. Imagine you start with 100% of your radioactive atoms, right? Now you wait for one half-life to go by. Boom, 50% are left. Wait for another half-life. Now you're down to 25%. That's half of the half that was remaining. Then 12.5%, and so on. It's this incredibly steady, predictable countdown that is the engine that makes our cosmic clock work.
And just to give you an idea of the timescales we're talking about, these clocks can be epic. The half-life of uranium-238, for instance, is 4.5 billion years. And it's no coincidence that that's just about the age of our entire planet. It's literally been ticking away since the Earth first formed. All right, so we have this perfect natural clock. The big question is, how do we actually read it? How do we use it to figure out the age of everything from ancient fossils to the planet itself? Let's get into the real-world applications, because this is where it gets really cool. It's kind of like having different tools for different jobs, right? You wouldn't use a sledgehammer to hang a picture. For things that used to be alive and are, relatively recent, up to about 50,000 years old, we use carbon-14. It has a nice, short half-life of 5,730 years. But to date something like an ancient rock, we need a clock that ticks much, much slower. That's where something like uranium-lead dating comes in, with its half-life of billions of years.
But wait a minute, how does this carbon-14 even get into a fossil or an old piece of papyrus in the first place? Well, the story starts way up in our atmosphere. Cosmic rays from space are constantly zapping our air and creating radioactive carbon-14. Then, plants breathe it in, just like they do regular carbon dioxide. Animals eat those plants. You eat plants and animals, and presto, this C14 becomes a tiny but very consistent part of every living thing on Earth. So as long as an organism is alive, it's constantly taking in new carbon-14, keeping the amount inside it perfectly balanced with the atmosphere. It's like a running tap. But what happens the second it dies? That's when the clock starts ticking. The tap is turned off, the organism stops taking in any new carbon-14, and the C14 that's already in its body just starts to decay at its own predictable pace. So by measuring the ratio, how much C14 is left compared to how much it started with, we can figure out with amazing accuracy how long it's been dead.
Pretty amazing, right? But this cosmic clock isn't just for looking back in time. Turns out, the same exact principles allow us to look inside a living human body in ways that are just incredible. So let's switch gears and talk about modern medicine.
This is the science behind a PET scan. It's genius, really. Doctors take a harmless radioactive isotope, one with a really short half-life, and they attach it to a simple sugar molecule. They call this a radiotracer. Now, what kind of cells in your body are super hungry for sugar? Well, really active ones, like cancer cells. So when this tracer is in your system, those cancer cells just gobble it up. They concentrate it. Then, as that tracer starts to decay, it sends out these little signals that a scanner can pick up, creating a 3D map that basically lights up exactly where the most active, energy-hungry cells are.
And this is what's so revolutionary about it. Think about it. An X-ray or an MRI, they show you the structure of your body. They show you what your bones and organs look like. A PET scan, though, shows you function. It shows you what your body is actually doing. It's the difference between looking at a picture of a car and actually seeing the engine running.
Okay, so let's just pull this all together. What are the big takeaways? First, radioactive decay is just nature's way of letting an unstable atom settle down and get stable. Second, the half-life of any isotope is an incredibly reliable, constant clock. And third, we figured out how to use this amazing clock to do everything from dating the ancient past to diagnosing diseases in the here and now.
When you think about it, it's this one single process that connects the immense age of our planet to the tiniest functions inside our own bodies. It really makes you wonder, doesn't it? What else will this cosmic clock help us discover? Thanks so much for watching.